All right. So welcome everybody. We got a lot of new faces. It's probably the mention of GANs and neural networks and stuff, and the spamming everybody that's relevant.
I didn't put it in the title on purpose.
So yeah, so welcome to, I think this is our second or third idea talk of the spring 2018 term. I am, for those who don't know me, I am John Erickson. I'm the one that's been spamming you. I'm the Director of Research Operations for the Rensselaer IDEA. And we have, I sort of host and coerce a series of Wednesday evening events throughout the term. We have, the Tethos World Constellation has TWED Talks, which are held down in Winslow. We have IDEA Talks, which are these informal talks. They're meant to be informal discussions of methods and code and that sort of thing. Here, we also have monthly RPI-R users groups, or R Pirates meetings right here, where we also have pizza. So I'll turn the floor over to Andrew shortly. This is being recorded and streamed. Just keep that in mind. You're welcome to ask questions as we go through, but just keep in mind that we're going out live, and it's being recorded for posterity. And without further ado, Andrew Yale. Thank you.
Yeah, feel free to, as I go along, interrupt with questions, just in case I gloss over something that is not self-explanatory. So yeah, I'm going to be talking about using generative methods for privacy-preserving synthetic data generators. So basically, what does that mean? Kind of where the motivation lies in this is mostly in medical data. So medical data, for instance, is heavily privacy protected, HIPAA, if you've ever heard of it, in the US. And so you can't really just share medical data, and then therefore it's kind of hard to do research on medical data without having some sort of access working for a specific company, something like that. Another application beyond kind of the scope of what we're doing, but like could be applied, is things like government confidential data. I mean, to varying degrees, that could be used within the government, where you want to have some sort of different levels of privacy and share to parts of the government without having to share the exact data. You could share it, the synthetic data that's similar, so that everyone can have an idea of what's going on. Or even things like private companies running contests, like the Netflix Prize contest was kind of made this famous, but publishing data that's not truly giving away their customers' data, but gives a good representation of it. Or even smaller scale things like interviews. So, like I said, we're mostly going to talk about the medical data application. That's kind of what I'm working on. But theoretically, these methods should be able to be applied to many different things. So, medical data has been studied for years. It's not necessarily new. I mean, it's become newer that you can have as much access to electronic records. I mean, the medical profession is notorious for handwritten notes and stuff like that aren't as easily transferred to the computer. But the data has still kind of been there. It's just behind the wall of things like HIPAA. So yeah, access to data is very limited. So and because of this, the training process is pretty costly. Bringing on a new member to a team in a company, it takes them a while to train on this kind of data because they may never have seen this kind of data before. They might be a good data scientist, but they may have never dealt with like in-depth medical data just because there was no availability. So a solution that we're proposing is basically teaching classes at RPI, for instance, using this synthetic medical data, and therefore they're more marketable to companies that use medical data, as well as they just get more experience in different types of settings. So the process for this, first things first, we're going to create a privacy-preserving synthetic data generator. Sounds easy, right? Second thing is then to take that into like a sandbox environment that restricted to health data that's only allowed in the sandbox. Train this generator, then pull the model out and be able to generate data as much as we want, and use it in the classroom. Really, what I'm going to be talking about in this talk is creating the generator, but just kind of to know why we're doing this. So creating the generator. So what I'm going to be talking about today is generative adversarial networks. There was a talk, I think, last year about these in general. So this is, I guess, drilling down a little bit deeper on the specific application of medical data. But other things you could use, we're also looking into things like causal generative neural networks, which is kind of interesting in a different, it's not as adversarial. You're trying to kind of discover the causal graph and then use neural networks to create data. And then you can also even just use things like variational autoencoders, which is another baseline that this the people working on this GAN were testing against. So what is a generative adversarial network? I'm going to go into kind of a brief overview of this. Is just like a standard layout of a GAN. Basically, we have our real samples up there on the top that are feeding in, as well as we have some generated samples that are feeding into this discriminator. So the discriminator basically tells fake data from true data, and then feeds that back to our generator as well as back to itself in the discriminator. And basically the idea is that the discriminator is trying to, is being trained to always, theoretically, always be able to tell fake versus real. But at the same time, the generator is trying to train to fool the discriminator into always thinking that the data is, from the fake data is real. So it's basically you're balancing these two things where the discriminator, you want that to be relatively accurate so that not just like everything goes through, but you also want the generator to be good enough to fool the discriminator a decent amount of the time. So this should kind of look like that, basically flipped on its side. But basically this is something called, they call it MedGAN, or medical GAN. Basically, it's somewhat similar. There's kind of some stuff in the middle there that I will talk about, but basically we have the real data right here going into the discriminator, and then we have our synthetic, our latent variables going into our generator, which also go into our discriminator.
I'm sorry, I don't follow this. What?
Okay.
So the data is X, and what is all?
Yes. So this is the real data, and so this is basically just random data pulled from like a normal distribution that goes into our generator, and then that also gets fed into this discriminator. And so basically, we feed data into the discriminator from both sides. It tries to tell the difference, and then we're kind of reinforcement learning, telling it, you know, you were right or you weren't.
So what is encode, decode?
So that's what I'm going to get to a little bit later, because that is the part that is different from like a normal, or at least the GAN depict the broad strokes description of a GAN. So this is, yeah, this is what this is doing is we're training an autoencoder in the middle here that we're going to use to help with our generator, which I will get to. So I'm actually going to start kind of at the end with the discriminator, which is the top part. And basically, this is kind of what it looks like. So basically what's happening with this is we have our batch of data, it's just n samples of our data, which in this case is got 1,071 columns. And so they're doing something called, they're calling mini batch averaging, which is basically they take their normal data, which is, you know, n by 1,071, and they're concatenating that with another matrix of the same size that is just all of it's an average, it's the average of all the rows repeated for all the rows. So basically on the left side we have the true data, and on the right side we have every one of these rows is just the average of all of the rows. And so the idea there is twofold. One is that it,
You mean each column entry in a row is the...
yes, is the yes. So all the columns are uniform.
Okay.
Yeah. Yes.
Just clarify whether you're looking at image data, patient.
Oh, sure. So yeah, sure. So this data is each row is a patient and each column is a different diagnosis. And so this is binary data where each column is a 1 or a 0, whether they were diagnosed or not with a certain disease or diagnosis.
This is comorbid data, but it's just diagnoses. It's just the only interesting. I mean, you can just randomly generate diagnoses.
Right.
It's about what?
Yeah, it's about the relationships. Yeah. So yeah, comorbidities. I mean, it's about why. I mean, certain diseases correspond with other diseases, basically, like you're saying, comorbidity.
He actually will get into that, be pretty interesting.
Yes.
How does like a medical student, what's the goal of like reading a column of, oh, this person has all these diseases?
Well, yeah, I see what you're saying. It is, this specific data set is slightly interesting, but not necessarily the end goal. The end goal will be a data set in our sandbox environment that will be more continuous data, measurements of just more things than just diagnoses. Yeah, but this was just basically, this is medical data that's available publicly. So this is basically what they tested on. In this case, though, you could do, different relationships between when you get diagnosed with a certain disease. Does that mean you're more likely to get diagnosed with other diseases? And the other thing is that these are diagnoses in the ICU setting. So it could also be interesting to look at even diagnoses that are just high heart rate or elevated heart rate or something like that. There are relatively mundane diagnoses that could indicate larger trends, theoretically. Yeah. So basically, they're inputting this double wide matrix into the discriminator, and the reason that they're doing this is because with the mini batch averaging, they're trying to maintain the sparsity of the columns. So by having these average values on the right side, they're trying to influence trying to keep in the fact that each batch has a certain sparsity, and ideally the entire matrix has a certain sparsity on all these columns. And then the other thing that they are trying to do is is part of the privacy part, which is prevent the generator from just kind of generating the original data back into or something very close to the original data back into the discriminator. And so basically, just kind of like a normal neural network, it's taking these and with weights, feeding it to one node, which in that one node is giving you a 1 or a 0, whether it thinks it's real or fake. And so, yes.
So this is the original game formula?
Yes. Yep.
So then these columns are discrete entries, though, no? So there's a 1 and a 0 in each column, right?
Yes. So it's actually, this is where it's kind of interesting because basically it's a 1 or a 0 if it's coming from the real data, but it's actually
no, in the drawing, but here you have entries on the left hand side. It's whether you have this disease or not.
Yes.
In each column. That's binary, right?
Yeah.
So it doesn't the original data formulation not look on discrete data?
I'm not sure. I didn't think that was a limitation, but okay.
I'll ask you.
Okay. Well, what I will say is the data coming from the generator is continuous. So yeah. But this is the way that they decided. So this part is straight from them, what they decided to do. And so they might not have taken that into account, and I was not aware of that. So.
Yeah. Can you explain why that duplication with the row average, why does that accomplish those two goals that you were talking about, like preserving the sparsity and not repeating, not just learning, memorizing rows, I guess?
Yeah, so basically, the way it preserves the sparsity is that ideally you want to fool the discriminator, you want to pass in something very similar into into here from the generator. And so if you can so even if this data is different, which it is almost bound to be, if you can get the match the sparsities relatively closely, this helps fool the discriminator. Whereas if you're also matching this, if you have already data that is different here, but this data is wildly different, that's really just not going to help in predicting in the end here. So the idea is that you will, by matching the sparsity here, it's more likely to fool the discriminator.
What about the privacy?
So the privacy. So they haven't fully convinced me on that one, to be honest. I mean, that's something that they put in there, but basically it's the idea is that I think by adding these averages in here, you are, again, if they match the average, they don't have to match this as much and still be able to fool the discriminator. So rather than if you put in just the raw data every time, the other thing is that the generator will learn to just match that row for row, because that's the way it has to fool the discriminator. Whereas if you add in this extra mini batch averaging, it can hit this as well as maybe part of this and be able to.
But then they seem to be competing with each other, because you're saying
Right.
You can match that side and it'll say, yes, that's good.
Yeah.
But then the other side, you're just learning the sparsity, right?
Mhm.
In some sense. And then the first use case for having that second set of columns there is to avoid that kind of situation. Right, because the second thing you said was that if it just learns the right-hand side,
Yeah.
because, you know, this privacy thing will say that, oh, it's good enough to match this,
Right.
right? So it doesn't care if you match on the first at all.
Well, I'm not saying it doesn't care. I'm just saying that it's not
Or it's not
solely
important.
caring.
Yeah.
It's not solely based on this, which is what a normal generator or a normal.
Actually, never mind. I'm
Okay.
confusing myself. Yeah,
Okay.
they're confusing.
Okay. And so basically, kind of to formalize what it's trying to optimize here. So the loss of the discriminator is basically penalizing if you classify the real data as fake, and penalizing if you classify the fake data as real. And then whereas the generator, the loss for the generator is going to penalize you if you classify the fake data as fake. Because the generator wants to fool the discriminator, whereas the discriminator wants to get everything right.
So, one node output. So basically, it's a sliding scale of whether or not it's real or fake.
Yep.
They're not doing discrete. Usually, when I've done this, I do 2 output nodes, one for yes, one for no, and I take the difference. And basically, so whichever one's greater is the answer, and then the difference is the confidence. They're not doing that. I mean, that's one way to discretize the generator too.
They're not bothering with that. They're basically kind of using it as like I guess more of like a confidence score in terms of like it's scaled kind of, and that's what this is doing to help penalize basically if you're getting close to if you're getting too close to the wrong direction.
So Jim, one thing that this does is this corresponds directly to trying to minimize the KL divergence between 2 probability distributions, whereas if you have 2 output nodes, I don't know if you really use the output, but you show theoretically.
Well, the output should be, I mean, they should be inverse of each other to get some of the loss.
I don't know. Maybe.
So usually with classifiers, you have to have
Not at this point.
all these other primary classifications to know it's trying to.
Okay, I'm just going to continue.
Yeah,
sorry. Okay, so moving on from the discriminator to the generator. So let's this portion over here. Basically, what this is doing is we're taking our sample size and it's sampling a random matrix from a random normal distribution, but of only size 128. And the idea is then it's feeding that forward through a neural network of 3 layers and then into a decoder, which I will explain the decoder in a minute. But basically, it's just using these. This itself is the generator part that's being trained and by the output of the discriminator, and then the gradients are directly going in here. Something else that they're doing in this paper is batch normalization and using shortcut connections. And so basically what batch normalization does is before each activation, it is normalizing each batch after you apply the weights. So you apply the weights, and then you're normalizing the batch, and then you're using your activation function. The idea there is that you're making sure that your weights and your values aren't diverging too much in one direction or another. And because of this kind of a generator, you could have a situation where you start to basically find something that will always fool the discriminator without actually generating a lot of different values. So you can keep fooling the discriminator by giving it something that you know will always fool it by like going in one direction or another. So this kind of keeps it a little bit more centered. Similar with the shortcut connection, what that's doing is that it's taking the previous round and adding that to the output of the activation. So you take this, this layer, this layer of nodes, you're activating it, and then you're adding the previous layer before you go into the next layer. If that makes sense. And so the idea there is that even though this isn't a very deep network going up 3 layers, it's also keeping you from diverging too much because you're keeping close to the previous layer. That part is not as necessary to understand for the overall scope, but basically it's generating from this this random noise, pulling this data, and it's creating 128 nodes, 128 nodes, and your sample size worth of data that's going to be fed into this decoder. And so, where do we get the decoder from? Basically, before we do all this, so that structure, what I explained before, is basically the entire GAN itself. But before we even create the GAN, we're going to make an autoencoder so that we can get the decoder out of it. So that's kind of this part in the middle that looked different from the original GAN. And so, kind of to explain what an autoencoder does.
Okay.
Yeah.
So what was the original GAN? Like, what was the sort of dimensionality of the data they were looking at?
So the original application was images. And somebody can correct me if I'm wrong, but I believe that they were just creating, they were sampling noise of the size of the original.
So, I mean, is
that not right?
It doesn't really matter.
Okay. Okay.
So the reason I'm asking is it seems like this autoencoder thing is just so that you don't have to predict, so like that G of Z can be low dimensional, so it's easier to fit a model.
Mm-hmm.
So is this specific to the medical data, or is this something that people used for the same?
No, I don't think this is specific to the medical data. This was brought in from, basically they combined a bunch of different parts of other research people have been doing on GANs. So I believe this was from a different paper that they pulled into this. So, but the idea here, yes, is that they could keep the generator low dimension, and then therefore what this does is, well, to explain an autoencoder, you have your original data, size 1071 nodes, which you reduce down to 128 nodes, and then you decode back to 1071 nodes. And the idea is that you can go through this network with a certain, any data that's 1071 wide, and you come out with something that is exactly the same as what went in. The idea there is that you're basically reducing the data down to a latent space of 128 nodes, or in this case, but it can be varying levels, and then being able to pull and being able to decompress it basically back to the original size. And so the idea here is that 128 nodes, just like our generator, we can put this decoder on the end of the generator so that we can decode our 128 nodes to the original size of the data. So basically, we pre-trained this autoencoder on the real data, solely on the real data, and then we just take the decoder part of it and put it into the generator, and then we can run our entire GAN. So and the autoencoder is just trained with cross entropy loss to ensure its accuracy.
Oh, so there's no regularization on any of the parameters in either the generator or the discriminator?
No, and that's something that I've tried to fix since. So this, this is kind of like the out of the box formulation that they wrote about, and future work that I have already started on and have some results from is basically just changing this to be a sparse autoencoder, because we already kind of know that this matrix is pretty sparse, and just having even 128 nodes we're generating too large of rows. But
And then
I'll get to that. Oh yeah.
Do you know if the authors of NetGAN are the first to use an autoencoder in a GAN like this? Or
I don't believe so, because I think that where they got this idea from was a different paper using this. But they might be. I don't think so. Okay, so now that I've kind of explained that, just to kind of go over, so I basically replicated on one of the data sets that they were using their results, and which I talked about last week a little bit. And so basically, one of the comparisons they did was this dimension-wise probability. What was very important to them was that all of the columns had a similar sparsity to the original data. And so the idea is that basically the sparsity of any specific diagnosis is the same as in the original data. So that you don't have too many people getting predicted with one disease that just isn't actually that common, and vice versa. Now, that being said, as you can see, there isn't any diagnosis that's that common. I mean, the highest is around 0.4, but you get the idea. And so basically what I'm comparing here is that for all 1,071 nodes, I'm comparing the sparsity of, sorry, 1,071 columns. I'm comparing the sparsity of the column in the original data versus the synthetic data. And so ideally, they should all be along that line. They're relatively close, but you can notice that there are a lot that are just really close to 0, which makes it relatively easy to just get close. It's that small. But another thing that they didn't really look at, and I chose to look at, was comparing the row sums. So kind of the other direction of this is that in the original data, there wasn't a single patient with more than 90 diagnoses, whereas I was getting rows from their original formulation up to 480 or so, which doesn't really make that much sense, because that means somebody had about half of the diagnoses that were possible. Basically means they're dead. I don't know. So that was something that they, and I think that where regularization comes into play is that basically our decoder was pumping up all these values high enough that we were just predicting certain rows to happen. I mean, this is a log scale. It's a little misleading, but there is any rows like this are definitely going to be wrong. And so another thing we looked at was kind of to measure the relationship between all these columns is the fact that, so it's binary data. What we were able to do was take the data and train and basically use each column as the predicted column and compute like a logistic regression using every column but one. So for each column, use the rest of the data to form a logistic regression and then find the F1 score of each of those. So this is something they did in the paper as well. But some of these columns are very sparse. And so when you split into kind of the testing and training split, as well as even in the synthetic data, there's certain columns in the synthetic data that it was able to get right and predict and fool the discriminator just by predicting 0 everywhere because the sparsity was so small. Which is why we get some of those values just along the bottom because we weren't even able to predict it because there weren't any actual values. So when there's a decent number of values, we can get pretty close, but there's some that are just kind of like are not there. And another thing that I looked at was doing a PCA, comparing the two. And so in the red is the synthetic data, and you can kind of see this long tail to this direction, which is roughly the percentage of those rows that are very kind of outliers to the rest of the data. But overall, it has a somewhat similar shape. And so the privacy results, so that was kind of looking at the accuracy. If you want to look at the privacy, so I mean, the first simple check is, did we actually generate any duplicate rows? Did we actually just like output any of the original data? And we didn't, which is good. I mean, that's a good first step. Like that's a pretty easy thing not to do, but you don't want to do that.
For single diagnosis though.
Sorry, what?
Single diagnosis.
Even for like
type 1 diabetes by itself.
Oh, Oh, I mean, oh, you mean if like one row had just that?
Yeah.
Doesn't that mean the same thing? I mean,
Yeah, so none of the synthetic rows that we generated matched any single original real row.
Right, but a boring row might match just, shouldn't a boring row match just because?
I'm not sure that there are.
So if you've got a distribution of type 1 diabetes in the population,
Mhm.
and a certain fraction of that's always doesn't have any comorbidity,
Mhm.
you're going to see basically exactly the same feature vector.
Part of what happened was all had comorbidities, and that's why it didn't match.
Yeah.
Yeah, I mean,
I think we probably should have gotten some matches before.
Right.
Yeah, that is true. And I mean, as we generate more data, I mean, this wasn't necessarily an exhaustive number of synthetic data generated. You would think that eventually you would have to overlap at some point, but you would, yeah.
but that actually raises an interesting thing. You could exclude the cases where there are, single morbidities,
Right.
And by constraining it in that way, requiring a certain minimum number of comorbidities, that's another end. I mean, you were looking at the other case where you don't have like an astronomical number of comorbidities, but you could also look at the low ends.
Yeah, that's true. That's true. So, yeah, I mean, the other thing I'll say about the privacy as a result is that we're still working on the accuracy of the GAN, so we aren't as concerned yet about some of the deeper dive into the privacy stuff. Some of the things that they did in the paper were if some of the columns of 1%, so they took 1% of the data and they took some of the columns and they acted like that was compromised data. And then they used the K nearest neighbors with the synthetic data to kind of fill out the rest of the data. And they weren't able to make it that accurate. I kind of lost the thread on that one because I didn't understand how somebody comes into half of the data.
So my basic feeling was, I kind of looked at that whole privacy stuff and I said, this is garbage. Because, my point was I'm not seeing anything from, I think for anybody to make a real definitive statement about the privacy of this, they should actually have somebody who's expert in evaluating, data for privacy, and for them to apply what are essentially ad hoc techniques. I think that's
well, exactly. And I just wanted to kind of demonstrate that they went through some of these, but I agree. There's a reason I haven't really gone through all these yet is because that I don't necessarily think that their validity is very strong. Because another one of the things they did was just take the Hamming distance of a small sample of the real data versus the synthetic data, which I also don't know what that necessarily proves because somebody else could build their random generator of this data and also guess rows. So yeah, I mean, it's kind of hard to make sure that you have the privacy evaluation correct, but obviously if you're going to go take this into a sandbox environment and then be able to bring the generator out, that is something that you need to think about down the line because the owners of the sandbox environment are going to want to know that their data isn't just getting out through a model.
So that you prove that you prove the discriminator sufficiently.
As long as they believe that is, that's the other half of it, is whether they believe that, yes. But yeah, no, I mean, and this is, yeah, I mean, I believe a couple years ago there was a anonymized data, medical data that was released or used with something that somebody was able to then de-anonymize. So it is a tough problem.
So, Andrew,
yes.
do we know in practice how useful these things are? These like anonymous data generated?
No,
because there aren't
any.
This is
So and there is a reason that the first application of this is classrooms. Whether the data is
it even good enough for that though? I mean, from what you've shown, it looks like it's not.
well, yeah, and I mean that is something we're trying to improve. But yeah, I mean, it is going to be hard to be that accurate, and I think that especially if we're concerned about the privacy aspect of it, it's going to be we're going to have to probably sacrifice some accuracy for maybe the privacy concerns, which might be okay in the setting of the classroom where you're just really trying to help people understand like
Right.
So making some logistic regression models.
I mean, in some sense, it seems like you're asking for a lot here.
Yes.
So maybe better to focus on one thing and try to capture that property of the data.
Mm-hmm. Yeah, that's true.
So he's not asking for it to be statistically identical. He's asking for it to be statistically similar, so that we can develop first in the classroom. We can develop pipelines, analytical pipelines that are on representative data. Okay, that's the first purpose is to do that. It's like a moonshot to go further and to actually produce interesting results by analyzing that data. That's not the first objective. The first objective is to have something that has utility for teaching the methods and not having to be totally crazy.
If you see the density estimation problem in that encoding space, which is hard, so it just seems like you're really asking for a lot there, as opposed to if you were trying to capture a particular property that's lower dimensional, then maybe that seems more feasible.
Did you have something?
Yeah, and maybe the fact that it is not perfect is actually a good thing, because data itself is very messy. Not half of it, but a certain percentage will be wrong half the time just because humans input things wrong.
Sure.
Right? So getting that maybe in a higher percentage is not necessarily a bad thing, because then maybe as a data scientist, someone is trained to look for that kind of messy data.
Okay, so I mean, go back to the row sparsity issue.
Mm-hmm.
That already says that that's not useful. I would assume.
Yeah. No, I mean, and so one of the things that they did in the paper was they went to a medical professional and they showed them some of their real rows, some of their synthetic rows, and said, "What do you think? Can you decide?" And the medical professional, it was roughly matching. They had a box plot of it, but then there was definitely some that were just not passing at all, because I think the medical professional would give a scale, 1 to 10, what they thought. But there were some rows where there were male only and female only diseases, both diagnoses, one column, or one row, where the doctor was like, "Nope, can't be, not possible. Can't have that." So yeah, no, I think that there are definitely things that need to be thrown out or something like that. That ended up being, so the rows that are greater than 90, I think was close to 1 or 2%. Mm-hmm. So it's not necessarily huge, but they also throw off the sparsity when you remove them, because really kind of why those rows were there were kind of to preserve that sparsity that maybe that's averaging.
So, but my point is, you don't know what it is that you're trying to learn from the data.
Mm-hmm.
So you could imagine you looked at this row sparsity, you looked at the logistic regression, you could look at, suppose you fix those issues,
mm-hmm.
and then you come up with some other metric and you look at it and the data's bad, and then you go back and you fix it,
mm-hmm.
but
what have you done?
Yeah, what have you done? You don't know that you fixed everything, right? Mm-hmm. Presumably you haven't.
Well, and so some of the real the real application that we're going towards is kind of diabetes prediction and stuff like that, where we have a known relationship and stuff like that. This is a little bit worse because we don't have a relationship that we're looking for to exist. But the data that we want, basically just something that can generate close enough data for right now that we will eventually know this is a relationship we're looking for and that we're trying to create, but synthetically, and then yes, we'll be able to
check all those fake ones, right? We check all these classification problems, because there'll be some classification.
Yeah. So yeah, there are other data sets that we plan to use, but we need to kind of prove the feasibility on at least just something else first. So.
I just got an idea based on what you just said. Because what it's doing is it's generating data that's completely from another planet. So you should have some kind of thing that constrains what planet you should be on. And then you can just toss that data. Because it makes sense that randomly it's going to generate from outside of the space. So what if you had something that kind of said, like a filter at the end, or even part of the process that says, the data is supposed to be in this ball, for example. And anything out of that, the ball is, the sparsity has to be less than 5, or whatever, and then you could, there's some stuff that's just so bad, you should just go, and it's what's the domain of applicability? Yeah, so you could add an extra layer just to, I mean, that would even maybe fix this.
Yeah.
But he's also not even taking into account demographics and founders.
He's starting to do nothing.
Yeah, I know,
Zero
sorry.
and ones. I mean, we're a long way from that.
Yeah, so
Yeah.
once you put those in, it's going to see in the pattern that these are male or female, simply because that's all there is. And so the discriminator will basically pick up those rules as part of the process. So if anything is outside of those bounds, the discriminator will notice that it's fake.
But discriminators don't really know about like data. I mean, they're particularly bad at doing that applicability. I don't know, hardly any machine learning models handle doing applicability. They just interpret. They just go.
Oh, yeah.
Yeah. So I mean, it's a big challenge. So I mean, hopefully they would learn that, and ideally we had. I don't think neural nets are that smart. I mean, like a one that was logic based and stuff like that. I'm not sure neural nets.
Yeah.
It's not really big for that. Like the alternative is causal, right? That it would learn those rules and it would do it yourself. So it needs help. So you have to make it smarter, do what you do, and it needs help.
So talking about some next steps, which I think I already got a lot of ideas already. So, but yeah,
This doesn't include the new ideas.
Yeah, it doesn't include the new ideas. I didn't type those up yet. So one of the things we talked about was fixing large row sums. So I added, I changed it to a sparse autoencoder formulation rather than just a regular autoencoder. And so these are kind of the comparison of those. Doesn't look that differently there, but we can already see that it pulled down a decent amount of those outlier rows that were existing before. Obviously still not perfect, but this is where something like a filter could come into play, where we can just kind of remove some more of those rows. I was noticing though that this is actually fitting. If you look at some of the squared errors on this, this is actually, the sparse autoencoder is actually fitting better than the original one. So even though it's removing some of these large row sums, it's actually doing better than the original one, which is good, because that would be a concern that maybe doing something like this and removing these large row sums might make it worse because it's meeting those rows or something like that, but it's not. So I think that there's definitely, I mean, we've already poked enough holes in what they did already that there's definitely room for improvement from what they started with.
Hopefully they're not watching.
Something like control selection, where you basically have a number of distributions that you're attempting to match, and you do random control selection from the what's generated, so that it matches your, you know the original data should be shaped like that along this dimension. So you have just a number of those functions, and then you use, like when you're doing case control matching, you try to match along those distributions.
So Andrew?
Yes.
What happens if you try to do the discrimination in the latent space? Is that not a good idea?
I don't know. Good question.
Seems easier.
You're talking about the code, like the auto encoder produces. So then how do you turn that coding step?
Oh yeah, how do you generate the data?
Well, you can still put it through the decoder. The question is, if it looks similar in the decoded space, will it look
what's the
similar?
loss on the decoder then?
Well, isn't so the decoder is trained with it? I thought it was just trained on the learning.
So the decoder is trained beforehand.
Yeah, that's just trained on the learning.
So yeah, you could theoretically, if you trusted your decoder enough, you could train a GAN to just generate the latent space and then use the decoder.
It won't work though, right? Because then if you're training then the autoencoder to produce a new code, and you're trying to get that to be more similar to what the real data looks like, then you changed the code that's being produced in the decoding step doesn't work anymore for this new set of weights that's been learned in the
Right.
encoding course.
Right. So the encoder is changing.
You would, I mean, if you were trying to minimize the distance between the code that's being produced for synthetic data and the code that's being produced for real data, then you're changing the encoding portion of that. But
Okay, so I thought you start off with your training data, you learn your autoencoder, and you always use the same encoding for your training data. Does that ever change? The latent space that you're expressing your training data in, that changes?
No.
Okay.
Well, but you don't, after you train the autoencoder, you're not using, for the real data, you're not using the autoencoder anymore. You're just passing that right to the discriminator.
Okay.
And
But still, can you discriminate in the latent space? And then you have a fixed latent space, and it's just a question of learning your noise to whatever transformation to make it look like your training data in that space. You can do the discrimination there.
So that's the step in which you have to start updating some parameters in order to generate better data. Right? And then suddenly the code that you're learning to generate doesn't necessarily match the decoding.
Those parameters are a step to the autoencoder. If you go back to that slide, aren't they, like where you showed the generative network that takes the noise, aren't those the parameters you're fitting? Or what's going into the autoencoder? The ROLU stuff?
Yeah, you're learning that stuff, right? You're good.
Yeah.
So I mean, the way I'm thinking of this is like, think of it as PCA. You have your training data, you learn your principal components from there, and then you're just learning some model that changes your noise distribution from Gaussian to whatever.
Okay. What I'm saying is, how do you learn decoder or GFT for that top box?
Oh, that decoder is fixed, right?
No,
that's the same decoder.
What's generating your
G and Z is being learned, right? Isn't the decoder fixed? That's the decoder corresponding to your encoder.
Yeah, I'm not changing the decoder, or it's not changing the decoder each time. But you're saying if you went
so decoder so the two decoders there are the same.
Yes.
But you change it dynamically, right, as you train?
I don't believe so. I believe that the decoder is just pre-trained.
So how would the encoder and decoder be changing the autoencoder? How would that depend on anything but the training
data?
I don't believe that the way they have it set up is that it's training the decoder. I could be wrong then. All right, and that it's continuing to update the decoder as it goes along.
It is. You think it is?
I think it's not.
Oh,
but I'm not sure.
I don't know anything about him. So I'm going off of what I've seen.
I mean, I'm sure that it trains it beforehand, but I'm not sure that it updates the weights on the decoder as it goes along. I know that it updates the generator itself here, but I'm not sure that it changes the decoder.
The generator is just how it moves.
So if that's the case, then it's already doing what is described.
Well, except you're learning the discriminator in a higher dimensional space. So say, why not just learn it in the latent space itself? Save some work, maybe be more accurate, maybe be less accurate is the question.
But yeah, I mean, yeah.
So generate from the embedding, isn't it?
Pardon?
Generate from the embedding?
Discriminate on the embedding.
Yeah, discriminate.
Possible, or I could be wrong that it is updating the decoder as it goes to, and then in which case then it couldn't. But
If it was fixed, it's no different than taking the row sum or something. It's just a fixed vacuum and you put out.
right.
You can use that for your phone. If it's changing, then that would be different.
Yeah. Yeah. So next steps, better privacy metrics. We already kind of discussed that the ones that they were using weren't necessarily that robust. And then the other thing is that this is all on binary data. If we actually want to use real medical data, we need to make this work for continuous. They had a version of this that they were using counts. So basically all this data, you can also interpret this data as count data because there are multiple ICU visits for some of the patients. So right now it just kind of made it a binary decision whether they ever got that diagnosis or not. But there's also a version of this data where there's counts because there could have been multiple diagnoses in a stay or across multiple stays. But their counts version of this if you believe it, was even worse than this. So they were really focusing on the binary application for this version. So yeah, an accounts version would also even be different from a continuous data version. I think we. Are there any more questions? Yes.
So, as far as I know, the medical records are usually time series.
Yes.
And actually, a patient may have multiple visits.
Yes.
So but here, what you're trying to learn is just a single corrected or something like that. And instead of considering the connections between multiple visits. So I think a better result should be you can generate a series of medical records instead of just some single values. Because this kind of series can help the researchers or doctors to know how the disease of patients develops.
That's
So,
chapter 2 of this.
Yeah, definitely something we want to get to, but obviously.
So I think
with the
that
current limitations.
I think a simplification of what Corey is saying is you don't throw out the you somehow have to consider the identifier, the patient identifier. That's because that's what ties it all together. That's what links it together. And
We have to follow this disease process because it's a hard problem. I thought we were going to do that video.
and when you do the evaluation, suggest you to do something like
comorbidities with
time. And you use the real data to train some machine learning model and get the accuracy of some results. And then you use the synthetic data you generated to do this, to train the same kind of model and get the accuracy. If the accuracy is similar, that means you really learn the distribution of your real data.
So
instead of just checking the sparsity.
Yeah. So I actually didn't include that, but I did something like that. Basically, what I did was I created a kind of like a random model and added a column onto this data, where it would basically be all 1,071 rows plus a categorical column that was either 0 or 1 based off of just kind of like random weights or a random like logistic regression model across all of them. And I passed that new slightly larger or one column larger matrix into this GAN, and then I was able to predict it with the synthetic data, and it actually kept that relationship intact mostly. I have it currently, but it basically was able to keep that relationship, which was good.
What relationship?
I mean, it was just a fake column, but because of the nature of this data, there isn't like a column that is just like.
Oh, I see. Sorry.
Yeah, but with this fake column, I was able to keep the relationship this fake relationship that I had added there. I was able to keep that through the generating process. So that was definitely something that we'll probably use later when we actually have something we're trying to predict. Yes.
Do you have an understanding of the HIPAA laws and how these autoencoders can get really precise, and you could be generating similar real data eventually? So what are the laws of kind of trained models?
Don't know. Yeah, I'm not. I don't know that yet, but that is definitely something.
I actually don't know if it considers that at all. I mean, there's in general there's a lot of discussion about anonymization and requirements of anonymization and various techniques for doing that. But there's I mean, one of the things that we're going to have to deal with is simply getting the let's call it the algorithm out of the sandbox, out of the secure sandbox. Well, we can train this, but we're going to have to come up with criteria that's going to convince our partner that it meets their requirements for removing this, that it doesn't actually embody any of the data, because we can't remove any of the data from the sandbox. but we can, in theory, we could remove the model if it doesn't sufficiently represent. And if if by something it like identically represents, we can't do that. We have to be able to prove before we can, I mean, again, in theory, it shouldn't be a problem, but we're gonna have to demonstrate this in some way. We're gonna have to have some way to prove that it's not, it can't reproduce the data. Yeah.
Right, so if you want to prove it, you pretty much have to use differential privacy. Like, have you looked into like differentially private autoencoders?
I've not yet.
That might be a easy, but if you want to prove it, that's pretty much the state of the art.
Well, so it's
if
like,
you want to demonstrate it, there are other things you can do.
So,
what Alex suggested, working from the low dimensional embedding, would let you maybe show statistical indistinguishability between certain distributions. If you're able to look at low dimensional objects, because you're not going to be able to show statistical indistinguishability in high dimensional spaces.
so if I could sort of augment what I just said, so this is, I think this is one aspect of it, but there's another aspect. So there's privacy, but there's also ensuring that we're not embodying any confidential data. Okay, so this is pure. Forget about the fact that this is medical records. Okay, instead, think about that. This is data, which we can't. It's data that we can't represent outside of this environment. Okay, so I think yours is a very valid point. Even though their data is already double anonymized, there aren't. So we can't. We've got to make sure we don't preserve those relationships. That's your point.
So
but another.
What he said is good, where you can train a classifier for a specific relationship, see whether or not you can learn that relationship from the synthetic data.
I don't think that's
I think you can use some.
But if you have a specific relationship, you have to still with that.
So another suggestion is you can use some current methodologies that other researchers use in their paper, and then use their data sets and then train your generator, and then use the generated synthetic data to train their model. If you try, I mean, maybe three or four model, and then the output accuracy is similar, that means that your data can be used to train some other models. And then when researchers, so that makes the researcher not necessary to use the real data to train their model. That's the value of your.
Well, so, but that's what you did here. Like, for instance, the model that was preserved was the column sparsity or right column sparsity, whatever. But you saw the row sparsity wasn't preserved. You can again imagine like coming up with all of these different relationships and it preserves these, but then there's some relationship that it completely just destroys. So if you actually were trying to learn new things that you didn't already know, you don't have any sort of confidence that you're really learning something that's in the real data.
But that's if we're that's like the end goal if we're trying to exactly match the data, which I mean, can we do that and not output the original data? I think we're going to have to miss something.
But that's also that's not the objective.
Exactly.
You know, the objective is not. In fact, you could imagine that sort of modeling is like actually the reverse. If we were to actually match the results of a modeling to a certain extent, that means we have to throw out that synthesized data because it's too close. Because our objective is not to create a statistically identical set of data. That's not the objective.
Okay, what is the objective?
That is the objective again. So in your formulation, you have to have something that kind of takes that into account, right? So the goal at equilibrium, again, the discriminator should not be able to tell samples from the generated distribution from samples of the ground truth, right? So almost by definition, you're like fighting against yourself there in the sense that you have to, or you're not fighting against yourself, but you have to find the balance such that in the formulation, I'm training my generator to produce things that are different enough, but still representative of that.
I see. Yeah, that's a good point. That's a good clarification.
Just using like a straight, GAN approach to it in the original formulation, you're doomed to not achieve your own goal because it will learn to accurately represent that ground truth.
So I'm gonna call it. let's thank Andrew and thank you for all the excellent questions. I just gotta call it so you don't fall over. But you can continue asking questions of Andrew. I just want to